Hi, welcome to Math341, Lecture 33. What I want to do today is talk about a situation where some of the results we want to use are not available to us because the conditions are not satisfied. So when you're using the central limit theorem, what do you need to be able to use the central limit theorem? Or at least what are our conditions?
Finite mean, finite variance.
Finite mean, finite variance. What else do we need? Missing the biggest part.
Numbers of sample large together.
Independence. We often say independent, identically distributed random variables. The identically distributed, you can relax a little bit, but the independence is a crucial assumption. So what happens if you don't have independence? Well, the central limit theorem is terrific for analyzing behavior in the limit. We do have some weaker results that we can use when we can't use the central limit theorem. What weaker results do we have for random variables to bound probabilities? We have two. We have Chebyshev and we have Markov. And if you had to choose between Chebyshev and Markov, which would you prefer to use? Chebyshev. Why Chebyshev is better?
It's more precise compared to Markov.
Yeah, Chebyshev uses both mean and variance to get information, whereas Markov just uses the mean. Of course, because of that, Markov can be used in some situations where Chebyshev cannot. So what I want to do is I want to describe a problem from number theory combinatorics, and then the way that we attack this problem is going to be heavily probabilistic. And it's going to allow us to review a lot of our concepts and see the difficulties when you try to apply them. All right. So I'm going to talk about more sum than differences or sum dominant sets. So I'll give you a little bit of a history. I'll talk a little bit about some types of results. I'm not going to talk too much about constructing families because this is not a number theory talk. I will talk a little bit more about phase transitions. So have you ever seen a subject where you've discussed phase transitions? Physics. Solid, liquid, gas. And you see these phase diagrams where all of a sudden at some critical pair of temperature and pressure, your material can have this remarkable transformation and its properties become very different. Ice is very different than water. Water is very different than vapor. And so we will actually see some phase transitions. And then if there is time, I will talk a little bit about some current work that I'm doing with students, where right now we've spent the entire semester running some simulations, and we are almost 50% done with the simulations. And these simulations, these explorations, can actually be converted into a proof. It's basically an exhaustive analysis. So we are estimating because we know exactly how long it will take, because there's no complication as you go further and further. We will finish before the spring semester ends. But there's opportunities to find better ways to code this. One of the midterm questions involved a coding opportunity that will be able to be converted to a paper. If you're interested, let me know. All right. So I want to talk a little bit about some integers. So we're going to overload the absolute value sign, and we're going to use it to denote the number of elements. It's a reasonable interpretation of the absolute value of a set. So if I have a set of integers A, the sum set is the set of all pairs of sums, and the difference set is the set of all pairs of differences. It turns out a lot of problems in number theory can be reduced to studying sum and difference sets. If you want to talk about Goldbach's problem, every even number that's sufficiently large, 4, can be written as the sum of two primes. Well, that means if I take A to be the set of primes, what can you tell me about primes plus primes? Does that include all large even numbers? Twin primes Fermat's last theorem. Fermat's last theorem says if you have x to the n plus y to the n equals z to the n, there are no non-stupid solutions if n is at least 3. What's a stupid solution to x to the n plus y to the n equals z to the n?
X, Y, and Z are 0.
X, Y, and Z are 0. Or a little bit weaker, just one of them is 0. Just y is 0, and then you get x equals z. So we want x, y, and z to be non-zero. It's the only non-zero triples have n equals 1 or 2. Now, which do you think is larger for a generic set? If I choose a set of A of integers, do you expect there to be more sums or more differences, and why? And to give you some encouragement, you can actually make a case for either to be larger. Both can be justified. Any thoughts as to which one might be larger and why? what should you do if you don't have an idea?
Example?
Yeah, take a piece of paper right now and just choose a couple of elements, create the sum of the difference set.
I mean, the difference is probably going to be bigger in general because you can get like 2 minus 1 versus 1 minus 2.
Yeah, so 2 minus 1 and 1 minus 2, that pair 1, 2 generates two differences but only one sum. So that's a really good argument why you should have more differences than sums. Now give me a reason why you might have more sums than differences.
Like if you draw everything on a line,
Uh-huh,
the difference is like the distance between 2 points,
right.
but the sum like it can go to infinity.
But I'm giving you a fixed set of integers. You have a fixed set of integers, and you're looking at all pairs of sums and all pairs of differences. And what was just remarked is if I give you two integers x and y, typically x plus y, well, x plus y and y plus x are the same, but x minus y and y minus x are typically different. And they'll give you two differences, but only one sum.
If you have differences that are the same, so if you have like several differences.
Well, so that's a complicated thing as to when do we have repeated differences and repeated sums. So that becomes hard and depends on the structure of the set. But I'm using the word typically. Typically, x and y will give you one sum and two differences. When is the case when it will not do that? Not negative. So when will x and y not give you two different differences? When is x minus y the same as y minus x? When they're equal. So whenever you take a diagonal element, whenever you take I equals j, you get a1 plus a1, a2 plus a2, a3 plus a3. They're all going to generate new sums. But ai minus ai minus ai, same. It's going to be 0. aj minus aj minus aj, 0. So when you look at the diagonals, you're going to have 0, zeros. They keep giving you the same element 0. It's this huge repeated 0. When you look at the diagonals here, they can give you new elements. Now, if my set has n elements, well, I actually know him, so it's okay. If your set has n elements, how many pairs do you expect to have? So you have n elements, how many pairs?
And choose 2.
N choose 2, which is roughly n squared over 2 pairs. How many times are you going to have a diagonal element where I equals j?
N times.
N. So n over n squared over 2. So in the limit, very, very few of the pairs are going to be diagonal. So you expect the fact that the diagonals are giving you more sums than they are giving you differences is going to be a much lower order effect. And so I would expect most sets will be difference dominated. And so we'll say it's difference dominated if there are more differences than sums. We'll say it's balanced if they're the same. And we'll say it's sum dominant or more sums than differences, more sum than differences if a plus a is greater than a minus a. All right. So as we were talking, we expect a generic set will be difference dominated. So what's the first question you might want to ask?
What does generic mean?
So what does generic mean? And so we need to somehow choose our sets. So the standard model that people did for a long time is you fix a probability p, and you choose every element from 0 to n with probability p of being in your set independently. What's the most common value p people use? 1/2. Because if you choose p equals 1/2, another way of looking at it is every subset of 0 through n is equally likely, as well as each element is equally likely. Go back to thinking about the ABBA and that terrible divorce which destroyed music. All right. So one question you could ask is, what does it mean to be generic? And I'm telling you now that we expect a generic set to be difference dominated. What's another natural question you might ask? So a big part is you've got to learn how to generate questions. So I'm telling you, you expect a generic set to be difference dominated. What might you want to know?
Why?
So I've given you some idea of why. What else?
The size of the set?
I'm sorry?
The size of the set?
What do you mean? So how big is the difference set?
Well, is it like infinity? How many elements?
You basically say that as we go further and further and further, do we still see generic as being difference dominated? I mean, I gave you the reason before that we expect it to be difference dominated. So that should continue to hold as the sets get bigger. Yes?
How difference dominated?
So one is how difference dominated. Are you just barely squeaking by and winning, or are you typically trouncing the sum set? But there's a more basic question that no one has asked yet. Yes?
What percent of sets are
So what percent, or even a weaker statement, is there even one sum dominant set in the world? Well, with computers, it's not hard to do this. The first one was given by Conway back in the 1960s. It's a nice calculation to show that it has more sums than differences. Another early example, and then with computers, it's really fast to just generate a bunch of these and just see that almost all sets are difference dominated. But you can find sets that are sum dominant, and you can find sets that are arbitrarily large, and you can even build infinite families of these. Now, these infinite families are very sparse. Most of the sets are not in these infinite families. So one way of constructing a lot of them is to know that if you have an arithmetic progression as your set, then the set is balanced. And so I want to go through this proof because this is a really good way about how to think about problems. And again, most of you are not going to want to spend your life looking at stuff like this. If you do, I have openings for the summer, so let me know. But it's how do you attack a problem like this? What arithmetic progression do you think our set should be? So I'm telling you, we're looking at an arithmetic progression. What arithmetic progression? I need the starting number, and I need the difference. 1 and 1, or 0 and 1. Why can we assume that it's the standard progression 0, 1, 2, 3, 4? Well, because without loss of generality, if I have a set that's not, I can always rescale it, and I can always translate it. So if the starting value is not 1, if the starting value is 2018, just subtract 2018 from everything. All it will change is when I add two elements, the sum will now be decreased by twice 2018, and when I subtract, there'll be no change at all. So now I can assume that my starting value is 0. And then what if I had 0, 4, 8, 12, sorry, pause so long, 16, 20, 24? Well, then I could rescale everything by 1/4. And then that would rescale all the sums by the same amount, and it would rescale all the differences by the same amount. What does this remind you of? Where have we seen this idea? Right, this is the central limit thing. This is how we start. We standardize our random variables. This is one of the big takeaways. Whenever you're given something, try to convert it to a really nice form. And now we can just look at the set 0, 1, 2, 3, 4, up to n. All right? Let's calculate the sum set and the difference set. What's the sum set? I take numbers from 0 to n and I add them from 0 to n. What do I get as the possible values? Not 1 to 2n minus 1. 0 to 2n. 0 to 2n.
Oh, you can add,
Right, because my set is starting at 0. One of the terrible issues in the subject is some people start at 0 and some people start at 1. So when you're looking at papers, sometimes sets go from 0 to n minus 1, sometimes they go from 1 to n. So the sum set is just going to go from 0 to 2n. What about the difference set? What's the smallest difference we get? Negative n. What's the largest difference we get? N. So we see that a plus a is 0 to 2n, a minus a is negative n to n. Both have size 2n plus 1. So if you have an arithmetic progression, you're balanced. So one of the questions was, how much does the difference set beat the sum set? Here are sets where it's perfectly balanced. And the hope is, maybe if we tweak an arithmetic progression a little bit, we can win out and make it sum dominant. And so there's a lot of constructions that are like this. When you look at this set, it may not be clear that really there's an arithmetic progression going on that we're doing some things to. It becomes more clear the larger set you have. This is not a number theory talk. I'm not going to go into too much detail on this. There are theorems that allow you to construct things, and you can see an arithmetic progression lurking in here. There's lots of different constructions you can do. For a while, my students and I actually had the world record for the largest set largest family. We sadly lost the record. If anybody wants to help me regain that, that is a good use of time. I will skip this. All right. I want to talk about phase transitions. This is where things get really interesting and are related to what we want to do. So we've seen the slide so many times, I'm not going to bother putting in the picture. X is a random variable with density f of x means it's non-negative, integrates to 1, and the probability to take on a value between a and b is the integral from a to b. This is why we care about calculus. We care about calculating areas under curves because they are probabilities. So two quantities we always look at is the expected value or the variance. The larger the variance, the less information you have on what's going on. The smaller the variance, the more information you have as to what's going on. So whenever possible, you would love to have random variables with zero variance. While they are technically a random variable, they have another name. What's that name? Constants, right? It's really easy to analyze a constant. What's so nice about the central limit theorem is that we essentially have things that are converging. And when we're trying to get, estimations, for a lot of these things, like when we did the Monte Carlo integration, the error was like 1 over square root of n. That's getting very tight, and it's going to tell us what the area is with incredibly high precision and with incredibly high probability. We want things like that. All right. So here's the model we're going to be using for our sets. So a binomial model with parameter p of n. So each element from 0 to n is chosen to be in our set A with probability p of n. Okay? The easiest case is where p of n doesn't depend on n and it's a constant. Okay? But we might allow p of n to depend with n, so as n gets very large, maybe the probability is getting smaller. One of the reasons we need to do this is we don't want our set to have too many elements. If our set has too many elements, then essentially all possible sums will be realized and essentially all possible differences will be realized. And it's going to come down to the behavior on the fringe. So let's think back to rolling some die. You always want to have some intuition for what's going on. When you roll 2 fair die, what are the possible outcomes? When you roll 2 die. 2 to 12. What's the most likely one? 7, right? You'll get 7 1/6 of the time, and you'll get 2 and 12 only 1/36 of the time. So it'll be 6 times as likely to get something in the middle. When you're looking at possible sums and differences, the sums in the middle, there are so many ways to get them that to not get a sum in the middle, well, for each possible pair, you've got to be missing at least one element. And it becomes extremely probable that you have every element in the sum set in the middle. Similarly, for the difference set near 0, you are very likely to have every element. It's the extreme fringes that are becoming very hard. And that's where the structure of your set is going to make a huge difference. Those 1 or 2 elements missing at the extremes will affect whether or not the sum set wins or the difference set wins if your set is large. And it was conjectured for the longest time that almost every set is difference dominated, and in the limit, 100% of the sets are difference dominated, if you choose from the uniform model with a fixed probability p. All right, and so I was just remarking, here's a nice observation. The expected value of a plus a, the sum set, is 2n minus 11 elements. The expected value of the difference set is 2n minus 7. So you expect to have 4 more sums than differences in these models when p equals a half. Is that enough to conclude that you will always win, or with probability 1, you will have more differences than sums? Because the expected value is 4 smaller for sums than differences. If that's not enough, what information would you like to know? The variance. Imagine I tell you the variance is 12. Well, then there's so much fluctuation that I could see sometimes the sums being large and the differences being small. What if I tell you the variance is 1 over n to the 5th? Oh, if it's 1 over n to the 5th, then as n gets very, very large, it is called strongly concentrated about this. And this is a wonderful concept. It's called strong concentration. If you have 2 means, and you know that your random variables have extremely small variances, they are strongly concentrated, and they can't intersect. Well, they can, but with extremely low probability. You now might have to be log n standard deviations away up top and log n standard deviations down below before the sum and the differences will cross. And even by a weak Chebyshev, that's enough to say that this is not going to happen with a positive probability. So this is how we can attack a lot of problems where we can't solve things exactly, is if we show things are well separated, then we can say they are different essentially all the time. Right. So the big result is due to Martin and O'Brien back in 2006. And they proved that if you choose your set according to the binomial model with fixed probability P, that a positive percent of the time you actually have some dominant sets. This was a shocking result. All the intuition said, oh yeah, in the limit it's going to be 100% difference dominated. The numerical simulations, so few sets with some dominant. The data was a bit misleading. Now, the probability is around 10 to the negative 4. In terms of, I think they proved 10 to the negative 7 as a lower bound, and we now, you might have just filled the class. Is it back in focus?
Yeah.
Okay. All right, you are back to passing. So they proved that it's at least 10 to the negative 7. The correct answer, we believe now, is around 10 to the negative 4. It is a small probability. And this is one of the dangers, is when you do numerics, you might say, oh, yeah, I've proved that it doesn't happen with any reasonable probability. You've got to keep in mind what is your level of confidence. So how many of you have taken lab classes where you have to do all this careful data analysis? You've got to be extremely careful about this. How many of you have seen special relativity? So speed is not additive. If I'm on a train traveling at 100 miles per hour and I'm running on that train forward at 10 miles an hour, relative to somebody on the ground, I am not moving at 110 miles per hour. The difference between what I'm running and 110 miles per hour is so small that you will not be able to notice it. But at higher speeds, if we could somehow have a train going at 4/5 the speed of light with myself running at 3/4 the speed of light, right? Yeah. You're not going to see me traveling faster than the speed of light. The additivity breaks down. This does mean that Newton was wrong. But if you look at Newtonian mechanics, in the realm in which he had data, what he was getting for his predictions was very reasonable. But then in some extreme situations where you did not have data, you have no justification for saying what goes on at low velocities is going to continue to hold at high velocities. So here, this was a great result. And so, and essentially the proof is what I was telling you, is that any element in the middle for the sum set, you almost surely get. And any element in the middle for the difference set, you surely get. So what they did is they chose fringe elements. They fixed the first few elements of their set, then chose the next set random, and then fixed the very end of their set. So the left fringe and the right fringe. And then the sum set really boiled down to left plus left and right plus right. And the difference set really boiled down to things involving right minus left and left minus right. And by choosing those sets very carefully, they were able to come up with an infinite family that was sufficiently dense that had more sums than differences. So they took families of some dominant sets and then they just fattened them up in the middle. All right. So I want to give you a little bit of notation to handle the phase transitions. So if I write x similar to f of n, it basically means x is approximately f of n for very, very large values. So specifically, I could find epsilon 1 and epsilon 2 arbitrarily small, such that the probability I am either less than 1 minus epsilon times f of n or more than 1 plus epsilon times f of n is less than epsilon 2. So percentage-wise, I'm extremely close to f of n. So let's let S be the number of sums, D be the number of differences, S complement is the number of missing sums, and D complement is the number of missing differences. For a lot of problems, it's sometimes easier to study what you're missing rather than what you have. We get almost every sum, we get almost every difference. It's better to look at how many things we're missing. And so we want to compare S and D. We know the expected value of S is less than the expected value of D. All right. So I'm going to use a new model. I'm going to choose my elements with P of n, but P of n is going to have some kind of decay rate. So this is technical things of writing here. This means that P of n is not decaying as fast or faster than 1 over n. Okay? We are choosing elements from 1 to n. Imagine my probability of choosing an element is 1 over n squared. How many elements would you expect to have in your set? So you have the elements from 1 to n. Each element is chosen to be in your set with probability 1 over n squared. How many elements would you expect to have in your set? 1 over n. And 1 over n is approximately 0. If my probability of choosing an element is so small, my sets are going to be empty. I want to make sure my sets have elements. If my probability was like 1 over n, I would expect to have 1 element in my set. If my probability was 5 over n, I would expect to have 5 elements in my set. As by saying it's very, very large. Well, if I only have 5 elements in a very, very large set, almost surely I'm going to have more differences than sums. I want to have the number of elements of my set growing with n. And that's why I have this rate. I don't want p of n to decay too rapidly. This part over here just means p of n goes to 0 as n goes to infinity. It's not a constant. Yes?
Is that a 0 or an O?
This is an O. So this is math notation, means little o. This just means it's 1 over n is much smaller than this as n gets large, and this is much smaller than any constant. So Martin and O'Brien dealt with the case of a fixed constant. We want to make sure the probability is going to 0. So the probability that k is in A is p of n. And so what Martin and O'Brien proved is that as n goes to infinity, A is almost surely difference dominated if your p of n is a fixed constant. What I proved with my colleague Peter Hegarty is that if p of n goes to 0, not too fast, then there are different windows of behavior. And so we were able to be very explicit. So g of x is the following function. And we showed that there are twice as many differences in sums if we are decaying faster than 1 over square root of n. So think of 1 over n to the 3/4. If our probability is that small, we have twice as many differences as sums. And this is going to be the case I will talk about. This case where we are decaying slower. Sorry, do I just want to say slower or faster? Slower, yeah, slower than this. Is extremely technical. It has to use a lot of high-powered machinery in terms of strong concentration. This part is weak enough to be done with Chebyshev. And that's what I really wanted to show you, is how you can handle this. This part is painful. This is the interesting part. If you're decaying at the rate of c over n to the 1/2, then you get strange behavior in terms of how many different sets you have over the sum sets. It's still going to be a factor of 2, but the number is going to be depending very nicely on c. And you have this remarkable transition in behavior to what's going on. All right. So I want to talk a little bit about how to handle what's going on. And the real challenge is we're going to have dependent random variables. So for most of the semester, we have always been dealing with independent random variables. If you leave probability feeling that there are only independent random variables in the world, this is a horror. We have to talk about how do you handle dependencies. So anybody know any result we've seen just in passing that allows us to talk about dependencies? We only mentioned it, I think, one day very briefly. We mostly concentrate on the case when the variables are independent, and then the formula for the variance is very nice. The variance of a sum is the sum of the variances. What happens if you have dependencies? What do you have to use? Covariances. So we have avoided covariances. Now it's time to look at them a little bit. So here's the sketch of the proof. So x is going to be either the number of sums, differences, missing differences. And then step 1 is to calculate the mean. And then step 2 is to calculate the variance. And show that the variance is tight enough so that the two means are separated. Unfortunately, we can't calculate the variance. That's too hard. Instead of calculating the variance, what could we calculate instead? Well, if we calculate the second one, we can calculate the variance. So if we can't calculate the variance exactly, what could we do? We need the variance to be small to show that they're separated. If you can't calculate something exactly, what could you do if you can't calculate it exactly?
Get an upper bound.
Get an upper bound. So for a lot of problems, we don't need an exact answer. And this is one of the theoretical dangers, is to think, well, I can't solve it. We don't need to solve it. If we can show, I don't know what the true variance is, but I know the variance is bounded by 1 over a billion, okay, that's often good enough. So we will only need the strong concentration results in this regime. We will skip that. So we'll assume the probability is decaying faster than 1 over square root of n. Think of it as 1 over n to the 3/4. And we're going to use Chebyshev up the wazoo. All right, wonderful result. So for convenience, we'll assume the probability is decaying like n to the negative delta. If you want to think delta is 3/4. For this part of the talk, you should not be trying to follow line by line. You should just be trying to follow big, broad brushstrokes. How do we use this stuff? We're going to use independent, identically distributed binary indicator variables. So x sub n will be 1 if we're choosing the element n to be in our set, and 0 otherwise. So again, this is a great way to review all the stuff we've been doing throughout the semester and seeing how that all apply. So if we want to calculate the expected number of elements in our set, it's not a problem. Why? Linearity of expectation. The expected value of a sum is the sum of the expected values. Each one of these is a binary indicator variable. So we get the expected value is n to the 1 minus delta. Because we have n of these, and each one of them is n to the minus delta. So what's nice about this is, since delta is between 1/2 and 1, this number is going to go to infinity, but slower than n. All right, that's the mean. Very easy. Now we want to calculate how many pairs we have and how many sums we have, how many differences we have, and some bounds on them. So the claim is if you let O be the number of pairs, then with extremely high probability, just something that tends to 0, the number of pairs we have is in some large range, but it's on the order of n to the 1 minus delta. So that's the number of elements in our set, and then the number of pairs is going to be roughly that. All right, so the proof, one is just Chebyshev. Because they're independent, identically distributed random variables, we can actually calculate the variance in the cardinality of x. That's not a problem. The difficulty is the variance in the number of distinct sums and distinct differences. But if we want to just count how large is our set, we know the variance is small, and then by Chebyshev, this is many standard deviations away from n. And so as a good exercise, go through and use Chebyshev to show that this is very, very likely. The next one is, well, if we know how many elements we have, this is just going to be the number of pairs. It's just number of elements, choose 2. So that follows immediately. So we have a good count on how many pairs we have, roughly. Now we need to worry about repeats. All right. And again, f and g can just be made explicit. Just think of it as p1 and p2 are small and they tend to 0. We're going to show that the number of differences divided by the number of sums is 2 plus a very, very small error with very, very high probability. We're going to do this by counting how many differences we have and how many sums we have. If every sum was distinct, we'd be done. If every difference was distinct, we'd be done. The danger is when you have 2 pairs that give the same sum, or 2 pairs that give the same difference. All we need to do is show that the number of pairs that give the same sum is small, and the number of pairs that give the same difference is small. If that's the case, then we know, if however many pairs we have, each pair gives us 1 sum and 2 differences, essentially. So that's all we have to do, is we just have to show the number of pairs that give a common sum or a common difference is small relative to the number of pairs. So we're going to show D is twice the number of pairs, and S is basically just the number of pairs. And this just gives you the technical stuff as to what range of delta will things work for. All right. So the contribution from diagonal terms is lower order, and we don't need to worry about it. It's going to be of size square root of O in terms of number of elements. We don't have to worry. The difficulty is, what if you have 2 things that yield the same difference? So I'm going to just show you how to do that. Sums is done similarly. So we have, imagine m and m prime and n prime yield the same difference. One of the big tools you need to learn is how to write things down in a way to eliminate or to streamline the number of cases you need to look at. Without loss of generality, I might as well assume that of the 2 pairs, the first element is always the smaller one. And then of these 2 pairs, I can assume that m is less than or equal to m prime. I could probably say m is not equal to m prime, because if these 2 were equal, then we'll leave it like this. So I'm going to introduce a new indicator variable. It's going to have 4 indices, m, n, m prime, n prime. And it will be 1 if the two differences are the same and 0 otherwise. Is it hard to calculate the expected value of this? No. It's just a binary indicator random variable. But I actually don't need the expected value carefully. I just need a bound for it. And so I can trivially calculate a bound for the expected value. And now comes the interesting part, is just how do we get some bound on the variance? As long as we have some bound on the variance so that we can show with high probability the number of pairs that give the same difference is negligible, we win. All right, we can't use the central limit theorem, so I will take off the hat. It's fine. They're not independent. This doesn't mean that all hope is lost. It just means you have to be more careful. Here's a nice result. The variance of u plus v is at most twice the variance of u plus twice the variance of v. So I'm not assigning homework this week. That's a great problem to prove. You could then ask, do you have to use the number 2? Is it easier if I put 4 or 10? Would that make the proof easier? What's the smallest number where this is true? So I write my y's as a u plus a v. And it comes down to whether or not there's an index in common. So for instance, maybe n equals m prime. And so maybe I only have 3 indices, and my indices are not distinct. And so now when I do it like this, I can now analyze each one of these. And now the variance of u will be the variance of these plus the covariance of those terms. And so we have at most n cubed triples. We can calculate the bounds on the variance. And now we have to work on the covariance term. I will just leave it as a slide like this and just say, you just go through it and you roll up the sleeves. Well, it's going to come down to, do I have any indices in common between these two terms? Are the indices distinct or are the indices repeated? Fortunately, there's only 8 indices at play, so I can go, all 8 indices are distinct. 7 indices are distinct. This is where it's nice to have lots of co-authors. Sadly, this was not a case where I had co-authors, so that's all right. Roll up the sleeves, you do the calculation, and all you have to do is get an upper bound. And we get that the variance is so much smaller that we're in no trouble. All right. So I'm going to skip the generalizations. I'm going to jump to the following very strange plot. So what do you see that looks strange about this distribution that is different from almost every probability distribution you have seen? Yeah, there's a dip. This is not goes up, goes down. Goes up, goes down, goes up again, and then goes down. So this is a plot of missing sums where we're choosing each element with probability 1/2. And it was a massive computation, but we were able to prove that this is just a little bit lower than these two. Not by much. What other questions would you ask now? What questions might you ask?
Are there other dips?
Are there other dips? So for instance, does it go down monotonically like this, or does it bump up later? We can't prove it doesn't bump up later. We can prove that there is a dip there. What other questions could you ask? So this is looking at the sum set where p equals 1/2.
What does the dip tell us?
What does the dip tell us? And so there is a reason, there is a dip at a very specific integer. Why is it at that integer?
The mean?
There's a more basic question. So this is what's going on when we are choosing our elements uniformly with probability 1/2 for the sum set. So there are 2 natural questions you could ask.
What happens when it's not 1/2?
What happens when it's not 1/2?
And when it's not uniform?
Okay, not uniform, excuse me.
If you look at the evens and the odds separately, there's no more dip. Like that difference happens just because one's even and one's odd.
Yes, and so it could be a parity thing, and there are sometimes, I've got some stuff in Zeckendorf decompositions where you actually have 2 distributions superimposed. And if you split them into the evens and the odds, then each one is a geometric, but it's like two merged geometrics. So that's a really good observation. The other thing is what happens with the difference set. No one has done any work on the difference set. So if anybody is interested, this is a great project. What makes the sum set so easy is when you're looking at missing sums, it all comes down to what happens on the fringes. So you can look at left fringe plus left fringe and right fringe plus right fringe. Well, you can pick a fringe and analyze it. And then you just take all pairs of fringes, but each fringe has been analyzed independently. For the difference set, you have to choose two fringes and subtract them. So it basically squares the computational complexity. So right now, the calculation we're running is to look at different values of p. We should have done this initially, but there's actually a way to code this using vectors to handle all p simultaneously. When you look at each fringe, you look at how many sums and differences it has, and then you weight it by a polynomial involving p and 1 minus p. So you can handle a huge number of cases simultaneously. Okay, so here is a plot of the distribution of missing sums for various probabilities. And then one question is to see what happens to the divot as you change the div as you change. Can you have multiple divots? Is it possible that if p is sufficiently large, there will be no divots at all? And initially, when we tried to analyze this, we looked at what was going on when p was very close to either 0 or 1. And those cases were very easy to analyze. And then as you start getting further and further away, the arguments become more delicate. And so these are a real mix of theory and computation, where we can break things up into computations for the extremes and see how they piece together. We can do the sum sets very easily, well, we'll say relatively easily, because you can just view it as left plus left, and then right plus right has the same thing. So for left plus left, you can ask, how often am I missing 3 sums, 4 sums, 5 sums? For right plus right, it's the same thing. And then you just look at all pairs and multiply and take into account their probabilities. So I only have to look at just one fringe. For the difference set, I have to look at 2 fringes simultaneously. And that makes it a lot more work. All right, and then just to recap, this shows you that in a lot of situations, if you can't solve a problem exactly, it's often okay. We didn't need to get an exact bound for the variance. We have not used covariances that often. For a lot of problems, you can be extremely crude, and the goal is I just need some rough estimate. And so the variance of a sum, yes, if they're independent, it's the sum of the variances. But what if they're not independent? Really nice exercise. Prove that the variance of u plus v is less than or equal to some constant variance of u plus some constant variance of v. You can then try to figure out what's the smallest constant. That's just showing off to your friends. Oh, yeah, well, I was able to get. But there is some finite constant. For a lot of these problems, you have an n going to infinity. A finite constant's not going to matter. So I really want to take these last few lectures to just show you how everything ties together, to show you where it goes, and to give you an idea of some of the issues that arise and how you surmount them. Chebyshev is actually extremely useful for all of this. We could avoid Chebyshev by appealing to some very powerful, strong concentration results. But this is, in mathematics, inelegant. Right? For a simple problem, you would like to be able to use simple techniques. You don't want to have to use the current state-of-the-art machinery. And sometimes it's nice to get a sense of how deep is a result. All right.